So the formula for theta, which is depending on time and n iter processes, so x1, x2 up to xn, is given by d theta to be equal to partial theta with respect to t dt and plus summation of 1 to n, I running from 1 to n, partial theta with respect to partial derivative of theta with respect to xi and dxi plus, so double sum, so like I and let me say k running from 1 to n, so it's the second partial derivative of theta with respect to xk and xi dxi and dxk. So now I will consider particular cases for such kind of Ito formula. Now let's say my theta is only depending on two variables and time. Let's say if n is equal to 2, in other words my theta is the function of only time x1 and x2. So like my k will be running from 1 to 2 and my I will also be running from 1 to 2. In this case, my d theta, or I can write df, it is given by, so partial derivative of f with respect to t dt plus, so I will only need two partial derivatives like theta with respect to x1, so partial derivative of f with respect to x1 dx1 and like 2 n equal to 1 and 2, so partial derivative of f with respect to x2 dx2 plus, now here how many possibilities will be there, so my I and k will be running from 1 to 2, so like so partial second partial derivative of f in this case, because theta is taken as f partial xk and partial xi and dxi and dxk. So dxi and dxk, right? So I can open this double sum and I can write this formula as partial derivative of f with respect to t dt plus partial derivative of f with respect to x1 dx1 plus partial derivative of f with respect to x2 dx2 plus, now let me run my k first and keep my I as it is, so like I can keep my I from 1 to 2 and I will run my k, so my k can take 1 and 2, when k is 1, so it is going to be second partial derivative of f with respect to like it is going to be x1, I should have written it in the superscript rather than in the subscript. uh, okay, so x1 and xi dxi and dx1 plus partial second partial derivative of f with respect to x2 dxi and dxi dx2. Now when this sum will run over this and also this, so I will have two terms from here and two terms from here, so there will be four terms over here and I can write all of those terms now. So it is going to be partial derivative of f with respect to t dt plus partial derivative of f with respect to x1, so there is 1/2 as well in the formula, so 1/2, so here is 1/2 as well, so dx1 plus partial derivative of f with respect to x2 dx2 plus, now so when I is 1 it is going to be dx1 when I is 2, so it is going to be dx2 dx1, and when I is equal to 1 this is going to be dx1 dx2. So like there will be four possibilities, I can list them over here: 1 over 2 partial derivative of f with respect to dx1 square dx1 square plus, so like partial derivative of f second partial derivative of f with respect to, so like x1 and x2 then So it is going to be dx2 dx1 plus, then I will have second partial derivative of f with respect to x2 and x1 dx1 dx2. Of course, 1/2 has to be multiplied, and then finally second partial derivative of f with respect to x2 dx2 squared. So like I can simplify and write the formula, because this is a mixed partial derivative 1/2 times, and this is also 1/2 times, so it is going to be 1 over here. So the formula will read finally as following. So my formula for my f, which is given by time x1, which is depending on x1 x2 as Ito processes, and time, this formula should be given by df equal to partial derivative of f with respect to t. So like with respect to t dt plus uh, partial derivative of f with respect to like x1 dx1, partial derivative of plus partial derivative of f with respect to x2 dx2 plus 1/2 times partial derivative square second partial derivative of f with respect to x1 plus 1/2 times second partial derivative of f with respect to x2. So it is superscript. Now this is a square. Uh, so I had to write over here dx1 squared dx2 squared plus second partial derivative of f with respect to x1 and then x2 and dx1 dx2, right? So this is how the formula will read. But more specifically, if my x1 is treated as x and x2 is treated as y, and then my formula will be df equal to partial derivative of f with respect to t dt plus the partial derivative of f with respect to x and dx plus partial derivative of f with respect to y dy and plus 1/2 second partial derivative of f with respect to x dx square and plus 1/2 second partial derivative of f with respect to y dy square and plus partial derivative second of f with respect to first x and then y dx dy, right? So this is how my multi-dimensional Ito lemma for the function which is depending on time x1 and x2 looks like this, right? Now I will apply this formula on a very specific kind of function, and from there I will derive my product rule for stochastic differentiation. Define f of t xy to be equal to xy. So I will apply, this multi-dimensional Ito lemma over this. So what I need partial derivative of f with respect to t, which is going to be 0 because it doesn't depend on t. Partial derivative of f with respect to y, it is going to be x, and partial derivative of x with respect to partial derivative of f with respect to x, which is going to be y, and I also need second partial derivative of f with respect to x, so it is going to be 0, and second partial derivative of f with respect to y, it also has to be 0, because over here when you second time differentiate it is 0, and over here when you second time differentiate it is 0. But when you differentiate f, which is differentiated already with respect to y, and you differentiate it with respect to x, then it is going to be equal to 1. So here partial derivative with the y first and then x, or x first and y later, are going to be same. So like we have assumed that the fxy partial derivative of x with then y is same as y with x. So in this discussion, all of this discussion, okay, so now let's substitute all of these values. So my df should look like, so my f, because is given by x times y, so it should be equal to f with respect to t, which is 0 dt, plus f with respect to x, it is y dx, plus f with respect to y, which is x dy, and plus, so these are 0, 1/2 0, plus 1 half 0, second partial derivative with the x is 0 and with y is also 0, plus uh, so partial derivative of f with respect to y and then x is going to be 1 dx dy. So when you simplify, it is the dx dy is given by x dy plus y dx plus dx dy. So where x and y are Ito processes. So for two Ito processes, in particular, we like specifically we write x sub t. So it is a Ito process, and y of t, y sub t is another Ito process. Its product, the differentiation of its product is given by x sub t dy sub t plus y sub t dx sub t and plus product of dx sub t dy sub t. So Leibniz rule in the usual differentiation looks different from this. So you have derivative of f and g sem and then derivative of g f sem. You don't have the product of f and g's derivative, but in this sense you have got this one. Why? Now I want to differentiate the following. So I want to find out what is going to be w1 square plus w2 square. So I want to find out its differential. So I can write this w1 square as w1 times w2 1 plus w2 times w2, and then I can operate my differential on both separately because the differential is a linear operator, even a stochastic one. So then I can use product rule by treating this x and this y. So x same y as differential plus y same differential of x dy1 plus dy1 times dy1 plus this is x and this is y. So you again use product rule w2 dw2 plus w2 dw2 plus w2 times w dw2. So this is going to be equal to 2 times w1 dw1, and you know that dw1 times dw1 is dt by Ito table. This is 2 times w2 dw2 plus this is dt by Ito table. So it is equal to 2 times w1 dw1 plus 2 times w2 dw2 plus dt. This is the, which could be written as 2 common w1 dw1 plus w2 dw2 plus dt. So this is how you can compute the stochastic differentials by using the product rule. Let's also compute the differential of w power 3. We can do what? We can do this. So it's Brownian and power 3. So I can write differential of w times w square. So by using product rule, this is x, this is y. So I can keep x same and differential of my w square plus w square same and differential of w plus dw times dw square. But we have computed this one, which can again be computed by using the product rule, and it turns out that it is 2w dw plus dt, right, plus w square dw plus dw multiply by 2w dw plus dt. So it's the cube of Brownian and we are computing its differential. So this is 2w square dw plus w dt plus w square dw plus, when you will multiply this w with dw, this is dt by Ito table, and this is going to be 0. So now you can keep your dw terms together, 2w square plus w square dw and plus 3w dt or 3w square dw plus 3w dt, if I haven't made any mistake, where w is the Brownian, so you could keep subscripted t over here as well. So this is the differential of cube of the Brownian.